whether can you reach the optimum very quickly or will you take a long time, right? And I think there isn't too much theory on what is the right learning rate to use. I think right now, it's a little bit of a rule of thumb. You start off with some learning rate, but most of the deep learning algorithms assume that it is hyperparameter and you kind of tune your learning rate to essentially see that you reach the optimum slowly, right? So that's about learning rate, right? The second part is around, I think you were asking about mini batch, I think SGD, right? Okay. So, okay, so first you got the concept of a gradient descent, right? So gradient means essentially you're taking the derivative of the loss function, and typically a loss function is summed over all your training instances. Let's say you have a 50 million training examples, so you're summing over all the 50 million examples. So if you want to do standard gradient descent, which is also called as the batch gradient descent, right? You're computing the derivative of this loss function over all the training examples, which is not computationally feasible with the massive amount of data sets we have these days. Yeah. So in order to avoid that, what people proposed was something called as the stochastic gradient descent, which goes to the other extreme. It says that instead of using the entire data set, let me do the completely opposite extreme and just use one training example, right? Because think of always the loss function as sum of all our examples. I'll just pick one random example, compute the gradient with respect to that, and move one small delta direction in the gradient, which will help this training example, right? But as you can see that it's a very loose approximation to the true gradient because you actually looking at one example, right? So this can lead to a very noisy estimate of the gradient, doesn't converge faster and all those. And that's where there is a in between, which is called as the mini batch stochastic gradient descent. So in practice, when people talk of SGD, they're essentially talking about a mini batch gradient descent where you take a batch size, right? So for example, 256 examples. So you take random 260 examples, compute the gradient with respect to that, and then do your regular gradient descent. That's your mini batch gradient descent. Yeah. So that's sort of yeah, I think that's the main concept of. But I think the surprising thing is that though this looks very among all a million samples, though this looks very noisy, surprisingly most deep learning algorithms just rely on that and they converge very nicely because and then you sort of do this for one batch, do it for second batch, do over all the examples, and that is called as one epoch. And then you go over back to the training set again and do multiple epochs, and that's essentially your training loop. Yeah. So yeah, so that's the part one. And of course, I think this is not what is used right now. I think this whole area has evolved a lot. I think there are a lot of now modern optimizers. And if you want to read up, you should probably read up something around, I think briefly covered about it, which is Adam and Adam W. These are the state-of-the-art STD algorithms used right now. And they bring in two kind of tricks. One is momentum, which is makes convergence faster. The other is, I told you about the learning rate. It makes the learning rate, the normal STD has a constant learning rate. Here you keep a different learning rate for every parameter where different every parameter gets a different learning rate, right? With these two optimization, Adam W sort of is now the SOTA algorithm you can use in your deep learning methods.
Right. Regis
Yeah.
versus Lasso came up a lot. So when do you pick each? How does L1 actually perform feature selection, and how do you decide how much regularization to apply?
Hmm. Okay. I didn't prepare. Let me try to answer because I think okay, so let me cover the basic concepts, right? So L2 is ridge regression, where the penalty is lambda into norm of W square, right? So there is always the L2 norm, right? That is called as a ridge regression. Lasso is called as the L1 regression, right? So it is plus lambda times norm of t- just the absolute value of W, right? There's no square. So this is called as the L1 regularization. Both L1 and L2 are some sort of regularizations because they are trying to say that, okay, I don't want my weights to go very high. So I'm going to put a penalty of lambda so that during training, let me put the lambdas very, by a priori, I'm thinking all the weights for all the features are useless. So I'll put that prior and I'll pull it back towards zero as much as possible. So L1 and L2 are two slightly different ways of doing it, right? So this again, maybe it also comes to this whole point about I talked about Huber, the MAE, MSE, right? The concept is roughly similar, right? So L2 is penalizing the square of it, and L1 is penalizing the absolute value of it, right? So there's a small little. I mean, you can in practice you can use both, right? both of them will drive the weights towards zero. But there is a small subtle difference with L1 is that L2 will try to push your weights to zero, but it will never make it zero. Very rarely it makes any weight to zero, right? So one cop out is that you use L2, but then you put a threshold and then you look at this all the weights which are less than say 1e minus 4, we call them as useless features, remove it, right? But then you need to make a choice of, okay, this, what should be that threshold so that the features are useless, etc., right? L1 has a slightly nuanced thing that as soon as it actually makes a substantial fraction of weights exactly zero, and that is because of how the L1 function behaves, yeah. So the reason why, I think I'll come to say, let me try to understand why that happens. But the reason wherever you prefer L1 is that you want to make sure that certain of the weights should go to exactly zero. Then you need to use L1 regularization. Yeah, that is the first part. Just to give you the a little bit, there is also something called the elastic net, which is between L1 and L2, where you put a linear weight of lambda 1 for the W1 square and the lambda 2 for the absolute value, which combines both of these here. How to pick the right regularization? I think the most common one is your cross validation, right? Or like a hyperparameter search. You take a value of lambda across a grid, right? And then you sort of apply it and then you do a k-fold cross validation. Yeah.
Right.
So, yeah. And the other one is sort of, I think there are some more algorithms, but they're a little bit more complicated where you can directly try to get the lambda. I'll not cover it, but I think straightforward answer would be a regularization, right? And why L1 makes it zero is because of the nature. I think you'll probably have to think of L1 as like a hypersphere, whereas L1, no, L2 looks like a hypersphere in a high dimensional space. L1 looks almost like a diamond shape. And the chances of your loss function hitting those corners is much higher for L1 than for L2. Yeah.
All right. Well, more to the next theme, which is
Mhm.
around cross entropy, BCE, and
Mhm.
log loss and likelihood. Right? Why do we use a cross entropy instead of MSE for classification? What does the negative log actually represent, and how does it connect to maximum likelihood?
Okay. Okay, so I think this also maybe I did not go very much in details on how actually the cross entropy loss came to be derived, right? But let's see how. But let's get the intuition of how this loss works, right? Yeah. So the loss essentially you have to think of it as it's always y log p, right? So if that is y is either 1 or 0, right? The true label, right? So if it is so it is y log p plus 1 minus y log 1 minus p, right? And there's a negative sign. So if you take the negative sign inside, it actually becomes y log 1 by p. Yeah. So if you look at it, if you are not familiar with it, say, let's say the entropy of any, let's say you take a coin and you toss it, right? So if you ask it what is the entropy of that distribution of a coin toss with probability p, it's essentially p log 1 by p, right? So essentially it is summation over whether plus 1 minus p, right? So this the minus is coming from the definition of the entropy, right? Yeah. So that's one, but the intuition is probably more important. But then the way sort of it works here is that let's assume if you know the true label is 1, right? Y is equal to 1. Then the loss is essentially what? Minus log p. So that is log of 1 minus p. So if you predict p is equal to 1, then the loss goes to 0. But if you predict p is equal to 0, then the loss goes to infinity, right? And that's sort of the main intuition, right? If you true label is 1 and you predict it is 0, you want a loss to go to infinity, right? But if you do that, I mean, no one can stop you, right? You can always take MSC and build a binary classifier. Most likely, probably it will work, right? But the loss is not a very formal loss there because here there if you take p equal to because you're already the function is finally predicting what is the probability that y is equal to 1, right? So it has to be number 0 and 1. So if you put p is equal to 0 and the true label is a 1, the maximum loss is what? It can be 0 minus 1 whole square. That is 1, right? But if you use the cross entropy loss, the loss actually shoots to infinity, which is essentially what our intuition is saying, right? Because if the true label is 1 and I'm saying it as 0, That's probably the worst error you can make, and I'm going to penalize it super high and make it to infinity. And that's essentially what the cross entropy loss captures, right? And I just explained with y is equal to 1. The same happens when y is equal to 0, and it just gets reversed, 1 minus y into log 1 minus p. Yeah. So that is the first is the intuition, right? The second is why is it called binary cross entropy is because uh, the true label can be either y is equal to 0 or 1, so that you can think of one distribution. And then there's a prediction that is coming. What is the probability that y, p and 1 minus p, right? So these are two distributions, and you're actually computing the cross entropy between those two distributions. And that's why it is called as a binary cross entropy loss function. That's the second intuition, right? Or the second way of understanding it. But the more formal way of understanding is via the likelihood function, right? So typically when you do any linear regression, logistic regression, or you're fitting any model in a probabilistic sense, you are computing the log likelihood of the data, right? So and we want to minimize the negative log likelihood, right? So one way to think about is the likelihood is essentially what is the probability of observing this data, right? So you write a likelihood function over all the examples and what is the probability. Then you can actually write the log likelihood function, and you can see that the log likelihood for logistic regression, which is sigma of W transpose X, comes exactly to the binary cross entropy loss function. Yeah. So I skipped the derivation, but if you guys are interested, you should actually go and home and write down the what is the log likelihood for logistic regression, and you'll see that the final loss exactly comes to be the binary cross entropy loss, and also see the connection why is it cross entropy. Yeah.
Okay, perfect. I'll move to the next question.
Mhm.
How should we think about decision threshold in logistic regression? Is a zero point 0.5 always right? And how do you choose it when false positives and false negatives have very different costs?
Okay. Yeah, I think this may be easy because this is all I always we covered this in the accuracy metrics, right? The answer is roughly similar. So, uh, so logistic regression, there is a threshold, right? So if you make the theta is equal to 0.5 is a balanced threshold. Otherwise, you can always make vary it from 0 to 1, and then you get the range of the different kind of trade-offs. Yeah. So the default 0.5 threshold works when it's an ideal choice when the classes are balanced, right? Yeah. So this is optimally increased when the class is balanced, and also when you think your false positives, even if it is balanced, you would still want to use some other threshold. Why? Because your false positive, there are two kinds of errors, false positives and false negatives. If you think they're equally costly, then you go with 0.5, and probably that's optimal. But in most real cases, the importance of false positives and false negatives are very different, right? So they're asymmetric cause, that is one thing, and classes are imbalanced, etc., right? So in such cases, you always want to sort of try to do a tune your threshold, right? So first you train your classifier, take some validation set or training set, compute the FPR, TPR for all possible values of theta and compute the trade-offs, right? For the ROC curve, or if it is imbalanced precision recall curve, then you'll have to make a call on what is your, how much do you want to operate, right? Which FPR or what should be your precision recall you want to operate. Either you can say, okay, I'm willing to operate at this much recall, then you choose the threshold that maximizes the precision. Or you say, okay, I want to operate at this much precision, then I choose the threshold to maximize the recall, and that is the theta that you will use in practice, right? So the short answer is yes. I think you best plot the ROC or the PR curves, then look at what errors are important, then decide the threshold rather than using the 0.5. Yeah.
Perfect. All right. I'll move on to the next one, which is can you give us an intuitive picture of bias variance trade-off and settle the debate? Does adding more data always cure overfitting?
Picture of bias. Yeah. So okay. So I mean, you can start off with the build the intuition with let's say a simple regression model, right? So let's say you have a one-dimensional regression problem, right? So where you're going to essentially uh, have a sort lot of random samples, right? And I want to predict y is equal to f of x, right? So the question of bias and variance is not just about data, it's also about your model parameters, right? Which is how expressive your model is, right? So I mean, if you are have a simple linear regression model y is equal to alpha x, which is just a linear line, right? Then I think it has a very it's not it has what do you call it as low variance, right? But sort of high bias, right? The other extreme is you put a very high dimensional curve where it tries to pass through every possible point. Then you are actually doing very good on the training set, right? So that essentially your curve is passing through every possible point. So then you have but the bias is small because you're predicting correctly everything. But even one small thing can change the whole curve, which is essentially the variance, right? So the total error is essentially a function of both the bias and the variance, right? Yeah. So I think does more data always help overfitting, right? Yeah, mostly yes, but not always, right? Yeah. When
All
Yeah, I think again, if it is very noisy or mislabeled data, then probably you're more off, right? But in general, if your model capacity is fixed, more data will always help you. But there's also a small way of figuring it out. You can sort of look at your learning curves, which is essentially I mean, you can simulate, say, 100 samples, 200 samples, 1000 samples, and see what is your metric, let's say the AUC, right? And see how it sort of stabilizes. If it stabilizes, then it means that probably more data is not helping you. Probably you should invest in more features or more models, etc. But if you think that your accuracy is improving, then probably you can spend more efforts into collecting more data. Yeah.
right. Um, the next one is walk us through doing data prep right, what the validation set is for, how to split correctly, including time series, and how to avoid data leakage in pre-processing.
Okay. Yeah. So, okay. So this is the, I mean, this is a little bit of classical machine learning, right? So whenever you're training a model, typically you keep three data sets, right? What we call as training, validation, and test set, right? So a training set is where you use to fit the model parameters. Typically around 60 to 80% of the data you use it for training, or rather 70%, right? By theory, if you go that, right, anytime you report a performance on a test set once thing, you're always leaking something. Right? So almost think of your test set as something that you kept in a vault, and it's going to be expensive to remove that and just look at the performance on it. Only when you think your modeling choices are done, you're done finally, you look at the test set, okay, this is what it is, and then it is, right? Because if you keep peeking at it too often, then you started overfitting on the future test set data. So that is so this one is called as the classical train valid test scenario, and typically you would use this when you have a lot of data, right? So reasonable data where you can afford to do this train validation test splits. The other paradigm when let's say you have very small data, right? Maybe in some medical things you've gone and done some study on some randomized test and you got maybe around 500 samples, right? That's all you can look at it and don't have the luxury of getting more data. There, you could essentially do the train test validation, but the test set end up so small that there is not enough power or training data. You want to use the whole thing for training. So there is, in those scenario, you go for this kind of k-fold cross validation set, right? Where you divide your data into k-folds, train on first four parts, validate on the final one, do this k times, and then take the average and report as the performance, unbiased performance on the test set, right? Once you're done, finally, okay, this is it. You would essentially take your entire training set and do one round of training and call this as the final performance on the training set of the model. Yeah. So that is that's that, right, about kind of the different strategies. And then of course you literally have to be, again, this depends on the domain, right? You always want to be a bit careful. You don't want to avoid leakage, right? And I think maybe there was an example called out around time series, right? So time series, again, without going into how that is, that you should never look at the future, right? Your training set, if you're doing a split of a time series, say you're forecasting things, make sure that you don't get any future thing into your training set, right? You should always look at all the features that are derived from this time, but all backwards, right? You'll never get to see the future, right? Also, sometimes some features uh, you, I mean, so there are other things you have to be a little bit careful when you're doing pre-processing, right? So, for example, let's say you're doing your training, but somehow, let's say, I want to sort of normalize all the features, right? I'm going to use some scalar, some compute the mean and the variance. I'm going to normalize every feature, right? I mean, ideally, you would like to do, you should not take the whole data set and do normalize. The best thing is you should probably do it only on the train split, right? So do all your everything, your normalization training before even you do the split, right? That's one way of avoiding leakage. Yeah. Yeah, I think, yeah, that's sort of it. Yeah.
All right. The next one is for robustness to outliers. How do you actually choose the delta in Huber loss, and how sensitive is performance to that choice?
Okay. Okay, so just a brief recap of Huber loss, right? Huber loss is somewhere in between the mean square error loss and the MAE loss. The MSE, so if your error is less than or equal to delta, it behaves like the mean square error, where it is half of delta error square. Or if it is greater than delta, then it is essentially your MAE, kind of a straight line, but there is a little bit of correction to make sure that it works smoothly, right? So what is happening is that for smaller delta, it behaves exactly like MSE, and for larger delta, it behaves like a mean absolute square error, MAE error. And this delta controls the transition point on where the things, right? So now the question is essentially, how do I choose this delta, right? So that you're robust to outliers, right? So, okay, the simplest answer is you can always take delta as a hyperparameter, which is essentially you try different values of delta, say from 0.1, 0.25, 1, etc. You define a grid and you do using the validation set, you tune this delta that minimizes your validation error, right? That's a generic prescription, right? The other one way to look at is essentially is you can look at something called as a residues, right? Which is okay. So what is a residues, right? You fit a model. Let's say this is a regression case, right? You're predicting something and you're doing a prediction. Residue is essentially the error y minus y hat, right? This, so you essentially fit a uh, look at the distribution of all the residuals, right? So you start, let's say you start off with a mean square error, not its Huber loss first, right? And you look at the distribution of all the residuals, and then you can actually set the delta to a reasonably, let's say around 95 percentile of the residuals, right? So this means that most of the errors will be treated as quadratically like MSE squares, but only the tail, which is above 95 percentile, will be treated linearly. But this distribution helps you make one choice of delta, right? So the practical choice would be you can look at fit MSE first, look at the residuals, make a value of delta, and then actually fine tune delta around that point using a cross validation approach. Yeah.
All right. I'll move on to the next question, which is before any modeling, how do you frame a business problem into an ML problem? And how do you decide which algorithm or model family to start with?
Yeah, I think this is a fairly broad question. I'll just yeah. So I think yeah. So most of the business, I mean, more likely, I think, okay. The first problem you would essentially frame is what is the metric you're going to report, right? Every problem has its own metric, right? So you have to sort of this. No, this doesn't come from the data or anything. This is a business decision that you have to decide. Okay, this is the metric that is important for me, right? So that is the first thing, right? The second one, you want to abstract this problem, right? Okay, I given you the problem. This is how you would solve. Should I abstract it as a classification, regression, or ordinal classification, or a sequence labeling problem, etc., right? That ML abstraction is fairly important finally to decide what is the kind of the approaches you're going to take. Once you define that, you will sort of decide, okay, look, the business is, this is the metric, this is the, and now I need to decide a loss function, right? So the loss function will be most likely a surrogate for the kind of one of the business, finally the metric you're deciding, but that probably you cannot optimize every possible loss function, but you'll have to make an intelligent guess on what is the loss function that I'm going to optimize this particular model on, right? So again, as a till here, I think we are making the key decisions. We're not even looked at the data and etc., right? So once you have this abstraction, the loss function and everything, that's when you start looking at a little bit of an EDA kind of start looking at the data. Okay, define what is your label, and then look at, okay, are there enough features here? Should I make more features? What are the different features? And that's when you do a little bit of EDA and try to define your feature set, etc. And only then probably you will come to the modeling choices. Probably that's the most simplest one. You pick one of the models and then you train it, right? And then you come to the hyperparameters, you train it using the validation set, and once you have, you report it. And after that, it's essentially a bunch of kind of iteration, right? So in terms of practical choices, uh, if you I think the probably the if you have a very small data set, let's say, and then most likely linear logistic regression are good choices. But out of the box, anything greater than 10K samples, probably XGBoost, LightGBM, CatBoost are the three go-to choices. Yeah. And all high dimensional text data, I think it's a different, like images, text, audio, NLP, they're all transformer-based architectures, right? So I think these are some of the core models that you need to be familiar with. Yeah.
All right, thank you. Next one is on based on linear regression fundamentals and assumptions, right? So for those seeing this for the first time, what are the key assumptions behind linear regression, and what's the intuition behind the Gauss Markov result?
Okay, I probably cannot cover Gauss Markov, I may have forgotten now, but let me cover the intuition between the linear regression, right? So, yeah. So I think the main first thing here is okay. So the linear regression is y is equal to f of x, right? W transpose x. That's it, right? That's essentially the model, right? But the first assumption, as usual, linear regression is a statistical model, right? So to make something statistical, I need to define what is the probability, what is the loss, what is kind of the thing, right? So what linear regression assumes is that the probability of y, that is the for any given feature, is modeled as a normal distribution with certain mean and certain variance, right? So the mean is your actual y is equal to W transpose x, right? And the variance is essentially the sigma square is your noise variance. So essentially you're saying that linear regression is just a linear function with Gaussian errors, right? So there are the first assumption is linearity. So why that is the first assumption. The second one is the errors are normally distributed with zero mean and certain variance. The third assumption probably is that all the errors are independent, right? Why does that help you? Because once you make all the assumptions, errors are independent, your log likelihood decomposes to the product of all the errors, and that's where you can write the likelihood, and then you'll see mean square error as the loss function. The fourth assumption, probably in statistics you'll read, is essentially on the homoscedasticity, or how does so the variance of error is constant across, I mean, where you are in this whole space of X, the error would be the same, right? Maybe if you think that there are certain bunch of examples where the error probably is more and some bunch of examples where error is less, then you're breaking the homoscedasticity assumption, right? Then there's also this whole, what are they called as independent features assumption, right? So for example, uh, I mean, let's say one feature is the height of the person, right? You cannot put another feature which is saying two times height of the person, right? And expect that something will break. If you look at the standard linear regression and then you try to invert the matrix because of the rank assumptions, things will break there, right? So I think, yeah, so these are some of the main assumptions that linear regression makes, right? So, uh, yeah, I think I'll probably skip the Gauss Markov result. I have not seen that in that slide. Yeah. If you had, I'll point it out to you later. Yeah.
Right. I've covered all the questions which came from the session and the themes. Right. I'm going to pick up questions from the chat now. So, folks, I see a lot of questions, and some of it might be repetitive. What I'd encourage all of you to do is, when you see a question and if you have the same question, please start liking it. So, based on the number of likes, I'll be able to pick that question and ask our scientist here. I'll go to the first question in the chat here, which is in production environments, data often comes from multiple sources with different schemas and features. How do ML teams perform feature integration and decide which joins or feature combinations are meaningful before training a model?
Uh, okay, yeah, I think this is, I mean, that's probably feature engineering, maybe depend on the job, is probably 80% of your job, right? Again, there's no hard and fast rule that's so mainly I think the first is to have an intuition, right? What are the things, features you think are vaguely relevant that can be predict something, right? You're predicting something and you have an intuition of, okay, these are the tables I need to look at, these are the tables, everything, etc. Right? So answer is maybe you can do an EDA and try out, okay, look at all the features, etc. But the simplest would be to use all the features that you have, and maybe you start off with some a gradient boosted algorithm, let's say either XG boost or a cat boost, and then you start pruning your features if you need to it, right? So I think more and more the modern kind of world, you don't need to do a very strict feature engineering. Most of the models are powerful enough to actually figure out what the features are important. So I think all your kind of intuition comes into actually mining what features you think are important for that task.
All right. I'll move to the next question. How is building ML models different between academia and industry?
So I think I'll maybe give a very subjective opinion of it is that in academia you probably do it once and you sort of leave it, right? You don't, no one comes back to you, right? So here in industry, I think the probably the biggest thing to realize that you are owning that model. That means you need to maintain it. That maintaining the model can mean a lot of things, right? That means you are responsible for the model. If the model goes down, what will you are the person they come back to you, right? Why is something, because some business is suffering, you're burning dollars somewhere, right? So then I think all your ML training comes into picture. Okay, am I underfitting, am I overfitting, did the concept drift happen, something happened, then you will have to do it, right? The second could be that, okay, look, now the model is becoming very expensive. We cannot maintain it. I'll have to simplify it, right? So then how do I go and simplify it, right? So I think all the techniques that you would learn in school probably are valid, but I think you'll have to little bit put a different lens to it and say that, look, I'm not going to do this model for just one time and get away with it, right? I'm responsible for it. I have to maintain it. And that means all the problems that come with it, right? Are all the classical problems people talk about in the textbooks, right? Yeah.
So, when monitoring data drift, if a feature stream is wide sense stationary, can we safely assume it is free-form concept drift, or can the joint distribution P of x slash y shift while keeping the first two moments constant?
Okay, I didn't understand this question actually. Uh,
I'll, uh,
maybe.
I
mm,
can I'll probably repeat that.
mm,
When monitoring a drift, if a feature stream is wide sense stationary, can we safely assume it is free-form concept drift, or can the joint distribution P of x slash y shift while keeping the first two moments constant?
okay, I don't know. I'll get back to you, right? Get me the question. I'll let me dig
Sure,
it up, right?
sure,
So
sure.
I maybe
All
it was
right,
in part uncovered. Yeah.
I'll move to
Yeah.
the
Yeah.
next one, which if a single decision tree overfits easily because it memorizes the training data, why does combining hundreds of them in a random forest completely eliminate that overfitting? Even though we are technically adding way more parameters and complexity to the overall model.
Hmm. Yeah, so I think I I am a little bit fuzzy on how. Okay, but my intuition says that you're not putting the same decision tree on exactly the same data multiple times, right? Then you get the same thing. So you're essentially looking at a very different. parts of the data. Maybe you're looking at different random set of features. You're looking at one way to look at is different kind of examples, different features, etc. Right? And that gives you a natural averaging across all the things so that you kind of the noise averages out and and that kind of reduces the weight and this comes to your classical bias variance trade-off, right? And that sort of buys you into make it more generalizable than taking thing, right? And in general, that's also another standard recipe, right? If you think one model overfits, you can always train it with different instance samples of that bootstrap samples of the data or different subset of the features and then average it to create an ensemble, which generalizes much better than just one thing, right? So that you balance off the bias variance trade-offs. Yeah.
Right. So another one is many ML models perform well offline but degrade after deployment. What is the easiest metric or signals you monitor to detect data drift or concept drift before business KPIs are affected? And how do you decide when to retrain versus redesign the model?
Yeah, I think okay. So the it's so the data drift is okay, so the business metrics take the precedence, right? The first is definitely you need to track that. That's the top level, right? And whenever you're seeing something going down, then you suspect something is going wrong for multiple reasons, right? But if the business metric goes down, it doesn't mean too many things, right? It could be there's a bug in the code and your features change. Maybe that's what happened, right? But at the same time, you need to have your own in-house metrics, what are important for the model, which is essentially what you are trained it for, right? Say, for example, the precision recall curves or the area under the ROC curve or some kind of loss function that you're tracking. The best way to do it is essentially to have always, it's again a question of, okay, so one is essentially if you have the luxury of always auditing your model, that's what we do in practice, right? That's while it takes time, so you'll always have a separate set collected at a regular time period. If you want to spend some time to get it labeled or some labeled data and constantly monitor the accuracy on that new data sets on the deployed model. That is one thing. The other slightly looser way to do is that you can actually look at feature track some of the important features or the scores, right? So you know how the distribution of the scores are. And now you can see whether in the last week, was there a very significant distribution? If the scores, the overall predicted probabilities and the distributions, if they're changing, then you know there is some drift. And if you go one level below and if you think there are certain important features, you can actually track the drift for each of the features, right? You can take this feature one and look at this is just how the distribution would look like. Maybe your percentiles are there. And maybe now within this, what is the percentiles look like? And those difference also tells you whether there is a feature drift. Yeah.
All right. The next question, we learned that supervised models optimize losses like cross entropy or squared error, but business ultimately cares about metrics like revenue, customer satisfaction, or click-through rate. In production systems, how do teams bridge the gap between optimizing mathematical loss functions and optimizing actual business objective?
Yeah, I think this again is a very complicated. I mean, that's essentially most of your job, right? So how do you balance that, right? So so one thing is most likely whatever the metrics that the business gets, you can always try to optimize it. Most likely they're not directly optimizable, right? So and that's when we need to use a surrogate loss. So I think the most all over sort of intuition, creativity comes into figuring out how surrogate loss so that it matches closely to the metric that I am interested in, right? So that's also a little bit calls upon what is the abstraction that you are going to use, right? So, for example, let's say you are predicting the how many ratings uh, book kind of product would get, right? One, two, three, four, five, right? So I mean, you could always say that I can use a multi-class problem, right? But then you're sort of ignoring the value problem that there is a ordering that one is great. I mean, five is greater than four is greater than two in one, right? So then probably a multi-class is probably not the right abstraction for this. Maybe you need to look at ordinal classification. So then you are sort of the choice of the model differs, right? And the choice of loss function differs, right? So again, my short answer is it's there's no clear answer how to do it. It's sort of very depends upon the problem domain you are in. But I think the most important takeaway is that you need to be cognizant of it, right? That there is a there is a difference between the surrogate loss and the one that the business cares. And our goal is to bridge as much as possible these two losses.
Right. Next, I think there's a very generic question which a lot of people are asking, which is with Claude writing code so well, what skills are becoming more valuable for an ML engineer? More like a career perspective question.
Hmm. Okay. So I think again, this is frankly, I also don't. It's an existential crisis which everyone is going through right now. So I don't claim that I have the perfect answer for this, right? Because I think it's a thing that everyone is sort of battling in terms of not just even ML, right? Any engineering, what the value do we bring in, right? But again, there are multiple. So the fact that we still, I think it's sort of. Again, for example, in internally that we use sort of Kiro a lot for in my sort of coding and everything, right? So it's becoming writing code is no longer sort of the bottleneck, right? I mean, it's the earlier you used to think, okay, I need to understand the syntax, I need to go and search for it, etc. Like stack flow, how to write this, right? So writing code is no longer the I'll go tease it at different levels, right? So writing code is no longer the bottleneck. Then what's our skill is essentially asking it what to write, right? So that definitely there is a lot of value in terms of ML engineers. Essentially, you just a single line out of the box will never work out anywhere, right? So which is essentially go and solve this problem. Maybe it works in some demos, etc. But any most of the problems I've seen, nowhere just a complete like a prompt, okay, go and solve this has never come up with the code, anything, right? So we sort of, my preference is I sort of, we work with the problem statement and that's where you create, right? You need to abstract out what is that you're going to solve, what is the formulation. Then use sort of Claude to actually write out the code, right? So that's thing, yeah. The other thing I think is a little bit, I think at least most of, lot of depends upon, lot of, we are in sort of the applied science team. We do spend a lot of work in in fine tuning, which is essentially be it supervised fine tuning or reinforcement learning based fine tuning methods, etc. Right? While there are a lot of cloud-based models that are very expensive, and that kind of job almost becomes like a prompt engineering job where you can write the prompt. But most production set out, they're either too expensive or the prompt is too brittle and does not serve our purposes, right? So we as a team do spend a lot of effort actually to take much smaller SOTA deep learning models, right, in-house and kind of sort of knowledge distill it from Claude or kind of fine tune it and various fine tuning strategies and then deploy it locally, right? So in my experience, roughly these are the two, I mean, kind of problem statements that our team has, right? Either you take the SOTA models and fine tune it for your problems and then use Claude for your slot of your coding examples, right? But I don't think we are still there where the Claude can completely replace most of the coding things, like the complete end to end. Maybe it'll be there, but right now we don't see it because I think we still see a lot of value in a lot of these kind of high level decisions that we have to take.
Okay, the next question is, what is the role of correlation and covariance in feature selection?
Correlation and covariance. Yeah, correlation is fairly standard, right? So essentially, if a feature value is important to a target, then that's correlation, right? How correlated your feature is to the target, right? Covariance is typically maybe you would compute across all your features, or if there are multiple labels, etc., and then you will sort of like figure out, okay, these two features are, how are these two different features related, right? I think it's a very, I think I need to little bit understand what is the exact question there, but I think a very high level answer, yeah.
Next one is, how do you balance model accuracy with inference latency when choosing between bagging and boosting from production for production systems?
Bagging and boosting. Okay, I probably cannot because I not used bagging and boosting in production. Was I not made that call? But maybe I can just comment on the high level, right? So between the how do you model accuracy versus inference cost, right? That's actually a challenge that we, at least a lot of the work that we do, we face, right? So because we have very state of the art cloud based foundation models right now which can solve most of the things, but if I sort of use it in production, I will just like exhaust the entire budget that I have for my team within a few days, right? So that's where I think we'll have to inference is some of the key things that right now what we do, which is essentially and different strategies, right? Where a common strategy right now is to take the cloud model, let's say the some of the SOTA models, and do a knowledge distillation to a much lightweight model that can be deployed in production that can run extremely fast. Inference is two things, right? One is essentially the latency, how fast can you serve some of the requests depending upon the problem domain you are in. The second, of course, is the cost, right? How cheaply can you get this thing done, right? While there is a lot of promise in the SOTA foundation models, they are neither that fast nor they are cheaper for us to use at the scale and the cost that Amazon can afford right now. And there's a huge value in essentially being able to understand, right, not just for us, but I think over across the industry, if you can make any LLM inference super fast, that is a very critical skill. Yeah.
All right. Folks, I think we are in the last minute. I'll probably take one last question. And I see most of you are asking questions on the program, which I will definitely cover. Right, I'll probably send across an email. You have a lot of questions on attendance, whatnot. You will receive a survey after this session, and you are expected to fill that. But I'll take one final question before we close the session. I'm just picking the right one. Okay, probably I go for this. When two models have almost the same metric, how do you break the tie and decide which one to actually deploy?
Uh, yeah, I think if your metric you're sure everything is clear, then probably both of them are equally same. Then I think it comes down to the other metrics, right? Of course, then how which I mean, my answer is simply these two things, right? There are typically three metrics that anyone cares in industries: your accuracy metrics, your latency metrics, and your cost metrics. If all three are same, then doesn't you can use any one of them, right? But probably you'll start off with, but you need to balance off with each of these, right? If your accuracy is same, maybe then I will choose the one which is cheaper cost, right? Or even if the cost is same, then I'll choose one which is faster, right? So each of them have a trade-off, right? So if you the final choice of the model actually not just depends on accuracy, but also on these three trade-offs.
All right, I think with that we come to end of the session. Thank you all for participating. You had asked a lot of questions in the when the model was playing, and I request to continue doing that because we will pick up the questions from there and then probably categorize into certain themes so that we are in a position to answer more questions in one probably themed approach, right? Along with that, I'll thank Vikas for joining in and helping sharing your knowledge with our students here. Thank you, Vikas. And final question regarding all of the program questions. Please do. I will send out an email with answers to most of your questions. So please do wait for my email. Thank you, folks, and have a
Yeah,
nice
thank
day.
you. Yeah. Thanks, Ratish. Yeah, thanks for all the questions, right? I also learned a lot. I mean, it's just some of the, you probably would have made up some answers, but mostly I think if you have any more questions to reach out. Yeah, thanks, guys. Yeah.
All right. Perfect. Thanks, everyone.